Okay. Hi, everybody. How are you? I am here again with the next portion from the properties of enzymes. The remaining portion today, I will present you the remaining portion. But before we proceed to our lecture, don't forget subscribing, liking, sharing these videos. Please also put your comments under this here, and let's go to our lesson, today's lesson. That is, today we shall see. Last time we have seen the physical properties. We have seen first general properties. Now chemical properties of enzymes. What are listed under these chemical properties as far as your textbook is concerned? For chemical properties, these are included: sensitivity. Sensitivity. I don't think some properties are confused here. Sensitivity, regulation, specificity, reversibility, and catalysis are the, as far as your textbook is concerned. I'm elaborating on some points and I'm presenting some points as they are as far as the book is concerned. Of course, now this is a graph that shows the chemical properties. I took it from your textbook: enzyme reversibility, enzyme specificity, enzyme catalyst, enzyme regulation, enzyme sensitivity. I don't know what enzyme catalyst. Let's talk. Enzyme sensitivity first. Enzyme work best of course, we have talked about this. There are factors which affect factors. Enzyme catalytic activity is affected by temperature and pH. Enzyme sensitivity refers to the fact that changed temperature, changed pH means changed activity. Activity of many body enzymes is most significant at an optimum pH of some 0.2, but generally ranges between pH 6 to 9, around neutral pH. We have talked about this in the physical property section. Uh, as far as temperature is, optimum temperature around 37 or 37.5 degrees Celsius, of course, for humans. This is human enzyme activity. Optimums. Temperature above 37.5 degrees Celsius and any alteration in pH may not only reduce the effectiveness of the enzyme, but also result in enzyme denaturation. Yes, denaturing agents, pH change and temperature change from the optimum. Therefore, enzyme sensitivity can be seen. They can lose their chemistry, chemical properties. The normal chemical property can be lost because of these changes, pH change and temperature change. The other, as a result of denaturation, the intra and intermolecular bonds between the enzyme molecules break, and heat and pH sensitivity is an enzymatic reaction to heat and pH, the acidity or basicity we have seen. Therefore, how can you define heat and pH sensitivity? That is an enzymatic reaction. How enzymes react to change in heat and to change in pH. Uh, how they react, that means by losing their three-dimensional shape. The second enzyme reversibility. This is clear, of course. Enzymes are the biomolecules that catalyze various metabolic reactions, including catabolic, anabolic reaction. We have mentioned this, yes. And in simple words, an enzyme can synthesize, build up new molecules or products, and decompose or break down different products, of course, or molecules. Therefore, they either catalyze building reaction or catalyze breaking down reactions. And the majority of the enzymatic reactions are reversible. Many enzymes catalyze reversible reaction, which means an enzyme can catalyze biochemical reactions in a forward and reverse direction. Digestive enzymes catalyze reaction in one way only, because we need this service only. You don't need your digestive enzymes join glucose molecule together and making starch, because you need the starch in your bread to be broken down into a simple sugar like glucose so that it can be absorbed. Therefore, digestive enzymes are one-way enzymes. They catalyze the catabolic reaction, the breaking down of large food molecules into smaller soluble forms so that they can be absorbed. Enzyme regulation, that is Regulation is the process of controlling the activity of enzymes by activator or inhibitor molecules. You see, the activity, the work of enzymes in the body should be regulated according to the need of the body. It should be on where it is needed, the product is needed. It should be kept off if the product is not needed. Therefore, regulation refers to the process of controlling the activity of enzymes by activator or inhibitor molecules. The enzyme function can be regulated allosterically. Some way of regulation is, of course, allosteric regulation. This works for allosteric enzymes. And I will elaborate on this. Other than the enzyme's active site, there is another site to which a regulatory molecule binds. This is known as allosteric site. This is not for all enzymes. Be careful. There are special groups of enzymes which are very important. Many enzymes in the respiratory pathway, like glycolysis and also the citric acid cycle. Many enzymes are allosteric enzymes. They do have many allosteric sites for allosteric inhibitors as well as allosteric activators, so that their process of energy production can be well regulated and controlled. Therefore, allosteric means other than. Allosteric site means other than the active site, of course, another site. Uh, a regulatory molecule may function as an activator or inhibitor. It binds to the region called the allosteric site. Enzymes that need metabolic regulators are called allosteric enzymes. These enzymes, allosteric enzymes that require metabolic regulator means chemical products. Chemical products. It could be end products which attach on the allosteric site and inhibit activity of enzyme by changing the shape of especially the active site inhibitor. The allosteric inhibitor binds to an enzyme's active site. The allosteric inhibitor binds to an enzyme's active site can cause slight alternation. This is, I think, miswriting, of course. The allosteric inhibitor binds to the allosteric site so that the enzyme active site can be changed. The shape of the enzyme's active site can be changed. You see, when allosteric inhibitor attach to the allosteric site, you see, allosteric inhibitor is attaching to the allosteric site, which causes change in the shape of the active site so that the substrate will not be bound to it. If the substrate is not binding to the active site, there is no change of substrate into product. This is the way to shut off temporarily for a time, the time being, to keep the enzyme inactive. When the product is needed, of course, the allosteric inhibitor comes out of the allosteric inhibitor site so that the active site will have normal shape and substrate can bind to the active site so that it can undergo catalysis to produce product. You see, therefore the allosteric inhibitor binds to the allosteric site. When it binds to the allosteric site, it affects the shape of the active site in such a way that the shape of the active site will be distorted temporarily, abnormal shape, which can't fit the active site, which can't properly hold the substrate, so that the substrate will not bind properly to the active site, so that there will not be change of substrate into product, so that the reaction is stopping for the time being as far as the allosteric inhibitor is attached. On the other hand, allosteric activators binding to the allosteric activator site so that the proper shape of the enzyme is maintained, so that the function of the enzyme will be increased, efficient activity of enzymes. The other chemical property, enzyme catalysis. Of course, enzymes are biological catalysts, we have said several times, which possess high catalytic efficiency. Underline this, catalytic efficiency. Really smart molecules, really. Enzymes are really super smart molecules. Unless we are talking some very few enzymes which are poor in terms of their efficiency, of course. Otherwise, the majority of enzymes are efficient, highly efficient, we can say. They can transform about, of course, this is very small number as far as I know. They can transform about 100 to 10,000 substrates per second. One enzyme, 10, 100, hundreds to several thousands, you can say, even some in millions, or even in several hundreds of several hundred millions of substrates are changed into product. And the reactions catalyzed by the enzymes show 10 raised to 3 to 10 raised to 8 times faster reaction rate in comparison to the uncatalyzed reaction. You see, when there is catalyst enzyme, the rate is upgraded or increased by at least 1,000 times, or at most 10 raised to 8 means uh, that is 100 million times faster. This is very important to keep life sustained, to keep life keeping on living, because life is nothing but the sum total of biochemical reactions that occur inside each cell. Biochemical reactions. These biochemical reactions should be performed in the appropriate speed. Appropriate speed. Speed is a matter of life and death. Speed, speed, speed. Therefore, as compared to the uncatalyzed reactions, catalyzed reactions are increased by a minimum of 1,000 times the rate, or maximum of 100 million times faster. Enzymes do not cause alterations in the equilibrium constant and increase the conversion of rate. They increase the conversion rate. The conversion rate. Conversion of what? Conversion substrate into product. Otherwise, they don't alter the equilibrium. The equilibrium of the reaction is not altered. They simply increase the conversion rate of the product, I mean the substrate into product, or if it's reversible, the product will be changed to the substrate, of course. The number of substrate molecules gives the product is called the number of substrate that gives the product is called the turnover number. Remember this. Uh, Catalytic efficiency of enzymes is measured in terms of turnover number. Sometimes they call it turnover rate. Turnover number can be defined as the number of substrate molecules changed into product by 1 mole of enzyme. Okay, the number of substrate molecules, not substrate mole, number of moles of substrate. No, number of substrate molecules, number of molecules of substrates, not number of moles of substrate. Number of molecules of substrate changed into product per unit time by 1 mole of enzyme is the appropriate definition of turnover number, and this is the measurement of the efficiency of enzymes, and this number is usually in in several thousands.